Hi to everyone on the call today. Thank you for joining us. My name is Peter Roberts and I work in the marketing team in Altair. So today's webinar, how Brompton Bicycle makes design decisions in seconds with Altair SimSolid. So just before we get started, just a couple of housekeeping things just to make the call run as smoothly as possible. So firstly, hopefully you can hear me on the call today. But we can't hear you if you've joined as a member of the audience. So, but we do want you to get involved and to ask questions. So if you do want to ask a question, there should be a questions panel likely to be on the right-hand side of your screen. And there you can type an answer and that will appear on our screens this end. And we have a Q&A session at the end of today, end of the session, where we will get through as many of those as we possibly can. If for any reason we do drop out of the call, which can happen on occasion, then we will restart it. So please just join back in if there's any technical problem like that. Then just join back in and we'll restart the webinar and pick up from where we left off. So just getting into the slides here. So our speakers today, we have Ken Welsh, co-founder of SimSolid and a member of the team here at Altair. He's going to be on the line here and joining us from California. And we also have Jonathan Heath, lead mechanical design engineer at Brompton Bicycle, based in London in the UK. So thank you to both of the team here for joining us and presenting on today's webinar. Just a little bit of a look at the running order of today. So we're going to kick off things with a quick audience poll. Then we're going to pass to Ken, who's going to give us an introduction to Altair SimSolid, a little bit of background on the product, and an overview of the capabilities. Another quick poll before we hand over to Jonathan, who is going to give the bulk of the presentation today, an overview of Brompton Bikes, Bicycle, the team makeup there, the design team makeup, and then a live demo of a SimSolid in action. And then we'll have a final poll and then go into the Q&A session at the end. So a poll to start off with. So what will happen if I kick this off now is you should see a poll appear on your screens. So the question is, which selection best describes your current role? So are you primarily working with CAD with limited or perhaps no use of CAE in simulation? Are you primarily working with CAE in simulation and very little use of CAD? Perhaps you're a team manager working primarily in CAD, or a team manager working primarily with simulation, or perhaps you're something else. You're coming from another part of the business. So we'll just give people a chance to answer that, and it looks like about a third of the audience is primarily working in CAD systems on a day-to-day basis, and around about 38% of the audience today is working primarily in the simulation side of things with limited use of CAD. So a good mix of an audience of the audience here today. So that's great. So thank you everyone who answered that. I'll close that poll now, and we should come back to the slides. And what I'll do now is I'll hand over to Ken, who's going to kick off the presentation with an overview of SimSolid. So Ken, over to you.
Okay, do you see my screen?
Yes, we do.
Let's see if I can get rid of that. Okay, great. Well, what I want to do to start was just give you a quick introduction to SimSolid, what it does and how it works, kind of things like that. You know, it's when people hear about SimSolid, they think, wow, it's probably just standard FEA, and it is FEA, but it is a little bit of a different paradigm. So SimSolid, you know, when we started the company, we had a clear vision, and we wanted to rethink how analysis was used primarily in the upfront design process. So what SimSolid is, it's structural simulation, but it operates, the difference is it operates directly on original unsimplified CAD assembly, so it can solve the full assembly. It doesn't create a mesh, it's a meshless method. And the goal is to provide results in seconds to minutes. So, you know, we thought, well, if we're going to really have an impact with simulation, we have to change, you know, certain things about how it's formulated and used. And this was kind of our vision that we've been sticking from the very first incantation of the product. The interesting thing about SimSolid, it was built from the ground up to be an assembly solver. And, you know, so we really had a vision of, let's not solve a simple one part, but let's really solve the assembly. And all our decisions on the product from day one were around that. Okay, so how do we do it? Well, we try to attack the two biggest roadblocks. Roadblock one was meshing. Meshing's tough, and it's especially tough when you're in a rapidly evolving design process. So, you know, you'll look at a lot of the CAD embedded tools, and they'll say, well, meshing's easy. And it is easy until when you have things where you have things with different scales, so assemblies with both big and small or thick or thin parts, and having to make the connections between those. Or if you have small geometry features with a lot of very small holes and bosses and things like that. On the lower right, another typical issue with meshing is you have, you know, a lot of odd face transitions or small or splinter surface patches that you have to mesh around to get a nice smooth mesh through. And, you know, these days there's a lot of lattice-based structures, so this extreme geometric complexity. This is also problematic for meshes. But, you know, one of the things that was most important for SimSolid was we wanted to find a way to elegantly and robustly connect parts together. So you'll see that a common thread in SimSolid is we spent a tremendous amount of time building connections and how to do that. And one of the things that a little bit unique is that we have a very robust way for handling small misalignment. So if you have, you know, a little bit of a gap or an overlap, we can still build a nice connection through that. And we adaptively solve to minimize the error of the traction forces in that boundary. So, you know, we get that connection, and we can also use, create a robust result there. The second thing we do is we use an adaptive solver. So what does that mean? Well, the workflow of SimSolid is the following. We bring in geometry. As we bring it in, we actually do part and feature recognition. So as it's coming in, we'll say, ah, that looks like a bolt, that looks like a nut, that looks like a washer, that looks like a through hole, that's a feature, that looks like a fillet. And we'll classify all that. Then we'll create our initial equation set, we'll solve it, and we'll do error analysis. We'll look at both global errors like strain energy and things like that, but we'll also look at local errors like the traction forces in the boundaries between parts. And we'll, based on the error analysis, we'll adapt the solution. We'll do a locally adaptive solution, enriching it where required, resolve it, redo the error analysis, etc. So we loop through the model and finally output results functions. So we're, you know, adaptive analysis is done by other FEA systems, but, you know, it's typically an option. It's not mandatory. For us, it's always on. And it's really, other systems is very rarely done for assemblies. This is only done for assemblies. So when you think about SimSolid, think about this meshless method, but it uses adaptive solver technology. Well, you know, the other hard thing about analysis is trying to decide what types of solution sequences you go after. And, you know, there's always a trade-off in terms of breadth, solution breadth versus ease of use. And we try to find the right compromise. You can see the things that we do. I'll just go over a few of the things. From solution standpoint, we do, you know, linear and nonlinear statics. We do modal analysis. We do dynamic analysis. It can be either time or frequency or random. We do thermal and thermal stress. We do inertial relief. We can do bolt pre-tensioning. We can also do, you know, result superposition. So we have a I think the basics of the solution sequence is covered. Materials, it's primarily an isotropic system. We have elastic plastic model for our nonlinear material, but think of it really as isotropic materials. The parts can be rigid, and the material, there is a material library, but of course you can extend that as required. An area that we spend a lot of time with SimSolid is connections. Now, think about connections. Besides the standard things of, bonded and sliding, and you can do separating with friction and things like that, really we spend a lot of time with connections in terms of spot welds, seam welds, bushings, rivets, other virtual connections. And these are, the reason we spend so much time here is these can be problematic in traditional FEA. In traditional FEA, making a spot weld or a seam weld, you have to do a lot of specialty elements, RB3s, and you need beams, and you need spiders, and there's all kinds of things you may have to do. For us, we solve it only in 3D, and you just pick the spot and go. We wanted to make it very easy to define these advanced connections. The one that's in red, adhesives, was available in our latest release. So we're still growing the connection set with every release. Results, we have what you'd expect, and you'll see those today. You can do contours and displace. You can do contours and animations, modal participation plots, XY plots. Reaction forces, that's something that's often overlooked, but we have a large set of reaction forces, contact pull forces, things like that. Okay, if you can have something that can solve an assembly and solve it in seconds to a minute, where does it fit? And we think it really best fits up front in the design process. People use it all over the place today, but we're trying to solve the direct CAD model as fast as possible. So that tends to lend itself to preliminary design. We don't focus, that being said, this whole who uses it is not so important as when it's used. So, we have a lot of design engineers that use it. We have a lot of analysts that use it. But I think the advantage, even for the analysts, is that they can now participate earlier in the design process than they could in the past. And I think that's important. And, it's not really, a lot of people say, well, if you can do all this, it just replaces our FEA. Well, in maybe some cases it does, but I kind of think of it as a complement. It does, what it does very well, and it does it very fast. But it's just another tool in the toolbox, and it complements what you may already have at your business today. SimSolid is a new code, and as such, there was a lot of, well, how accurate is it, how well does it work, and we've spent a tremendous amount of time on that topic, as you would expect. We have a verification guide that you can get and download, and has hundreds of problems that we solved, that all the standard types of tests. And here's an example. This is one with separating contact. And you can see here that we have, a very simple case, but you fix the base, you have separating between the two parts, and you just have a series of forces that balance there, and you can see if you can get that exact result. We do very well on separating contact. Now these are all the standard tests that everybody does, but there's other ways to look at the model. I want to just show you a couple more. One I thought was very interesting and just recently done was by NAFEMS. NAFEMS, in their latest benchmark magazine, had an article there say, designer-oriented software, is it accurate? And it's a little bit different article than you see in NAFEMS in the past. NAFEMS would typically take these very simple, well-defined models that have, reference theoretical solutions to compare it. So you do this very specific test, more like the tests that we have in our validation manual. But these tests were a little bit different. They said, okay, we're going to bring the model in as a design engineer would. So just bring it in and solve it, and then we're going to compare it. So they weren't just comparing the accuracy of the solver, they were comparing the accuracy of the workflow. And I thought, well, that's really interesting because, you know, a lot of times you'll hear people talk about, you know, is it accurate? Can it solve the right, can it get the right answer? And if you have a well-formed problem, yeah, you get the right answer. But the bigger question, and I think the question that Nathan's asked was, for the designer that just brings the model in, how well does it do there? So I think it was a very interesting read, and I encourage people to grab it and look at you know, what they said. One more test that I think it's good because it illustrates an interesting point was we had a customer was looking at a golf club head, and they wanted to tune the acoustics actually of the head. And we don't do acoustic analysis, but you know, modal analysis is a proxy that was good enough for them. So they wanted to get the modes very accurately. And the problem with getting modes on this, there's a problem. You look at this cross section; it's a very thin 3D structure, and it has varying thickness. So you have a choice. You can either model it with shells, which is, you know, quite an effort to build a really well-graded shell mesh there, or you can do it with TETs. And TETs, again, that's a challenge because putting enough TETs to the thickness to get the exact frequencies is a challenge. So this is a really hard meshing problem. For SimSolid, we just bring it in and solve it. So the question was, how did we do? Well, here was our model, and here is a traditional FEM model. The FEM model was almost 2 million second-order tetras. So, you know, it's a very dense model, but you needed that density to get the solution through those thin areas. For us, we just brought it in and solved the geometry directly. We used 6 solution passes, so this is a high-resolution number of passes, but we just said solve. And the results are, I think, are very good. You can see that we compare for the first number of flexible modes. We did a free modal analysis, and you can see we're spot on in terms of the frequencies and the mode shapes as well. The interesting thing was for us, we just brought the model in and just said solve. It took 9 minutes to solve. So open, solve, you know, adaptively, you get a solution. FEA, you had to bring in the model, but you had to mesh the model. You had to grade the mesh. You had to validate the mesh. And then you had to solve it. It took longer to solve. So it was a much longer process, and it was a much more error-prone process. There had to be you had to have more of a person in the loop looking at, you know, how well the model was prepared, et cetera. So I think if you look here, now, did we replace FEA? No, but if you want to do a quick what if, and I want to take that geometry, put a baffle in, change the thickness, you know, how does all those changes affect? You can do that in a practical way with SimSolid, which you really can't do in a practical way with FEA. So if you just want to play what if games, it's a great tool. If you want to do a final validation, yeah, maybe you can do that in your standard FE system. Okay, so with that, let's see. With that, I think I'll stop and turn it back over to Pete so Pete, there, you can take it back.
Thank you, Ken. So again, just before we get to John, we're going to do a final, a second poll question here. So again, it should pop up on your screen now. So John is going to talk a little bit about how Brompton Bicycles uses SolidWorks and how that links in with SimSolid. But what about your company? So the question is, what's your company's primary CAD platform? So some of these are a bit grouped together because we can only give so many choices here. But you working on SolidWorks or CATIA, Autodesk, an Inventor, Siemens NX or Solid Edge, Fusion 360 Onshape or Space Claim, or perhaps your company is using something else.
Peter, I'm not seeing the polar. Is it there?
Yeah, people are should be seeing that one, Ken. We're getting answers coming in, so we should be okay.
Okay.
So just one more, few more seconds on that. So it looks like, you know, vast majority of the audience here is on that SolidWorks and CATIA platform, about 55%, around 10% Autodesk, 15 Siemens and NX, and then around 15 or so percent of the audience are saying something else. So thanks very much for that. I'm going to close that poll now, and we're going to hand over to John, who's going to give us an overview of Brompton Bicycle and give us a live demo of SimSolid. So Jonathan, you should have control now.
I have, yep. So okay. Hopefully you can see that.
We can, yeah.
We can, good. Okay, welcome everybody. My name's Jonathan Heath. I'm the lead engineer here at Brompton, working in the special projects team within design. So first of all, let me give you a sort of brief introduction and background to Brompton, the company, just to put the design department in context, and then again putting how we use simulation and especially SimSolid in context here. So Brompton Bicycle, it was founded in 1975 by the engineer inventor Andrew Ritchie. He didn't necessarily come up with the concept of the folding bike, but he was given a folding bike called the Bickerton, which he rode and folded, unfolded, decided that it can be made a much better product, being an engineer by trade. So he spent some time developing his own folding bike, and the first iteration of that bike can be seen here. It doesn't look too familiar to the Brompton today, but you can see the general concept of the fold in the frame, the fold in the handlebars. So that was in the late 70s. Then fast forward into the early 80s, you can start to see the first generation of the Brompton bicycle with the hinge in the middle of the frame, the fold on the handlebars, and it was beginning to take shape. So during these years, he was really just starting to make them in a very small factory, and barely a factory, just a workshop under the arches in London. So very low volumes, selling to friends and family, and still trying to raise money to build his business. So it was very challenging, and through the 80s and then up into the 90s, he managed to refine the design, optimize the manufacturing method, and start to sell more product. So I'm going to fast forward now over those couple of decades to where we are today. So this is the Mark V Brompton. It's based very much on the existing design. So there's quite a few refinements around brakes, drive train, wheels. Still the frames. We have one frame size. It's still hand brazed in our factory here in West London. I've shown pictures here of the bike. It's not just a bike, it's a piece of luggage. So it has 3 fold states. So the back wheel kicks under, handlebars drop down, and then you have the folded format, which is effectively carried around like a piece of luggage. So during design and development, we're having to think of this in multiple states. It's not just a bicycle. So going back to the early days, this is a photo of the workshop. You can see Andrew Ritchie there in the foreground, assembling one of the bicycles. And then again, fast forward to today, we have our factory here in Greenford in West London. last year was a record year. We produced 50,000 bicycles. So we're manufacturing around 200 bicycles a day at the moment. They're all bespoke. So if you want to order a bicycle, you can go into a bike shop, ride one, see if you like it, and then go online and select through the thousands of different configurations, options, colors, gears, whether you have dynamo lights, racks, etc. And those are all built to order here in our factory. So that takes me on to the design department. So within our facility, we've got around 250 employees. And of that, there's around 12 design engineers. Now, what's important here is we don't have any dedicated CAE simulation engineers, predominantly because we don't have the resource to have that. We don't have the number of engineers to have that dedicated resource. So we've grown over the last this department has grown over the last 5 to 10 years in terms of developing our tooling team, to growing our design team within Core Bike, and then stepping away from Core Bike a little bit. I've been specifically involved in the special projects team, which is where we've invested heavily in using FE, developing new elements of the bike from a structural viewpoint. Just to give you a sort of idea of the range of engineers that design engineers we've got in our team. So we have a couple of industrial designers through product design engineers up to mechanical design engineers who are looking more at the structural engineering aspects of the product rather than the aesthetics. So what I wanted to do with simulation was to open it up to all of the design engineers, whether they're working as an industrial design engineer from concept, or whether they're evolving the structural elements of a new frame set design. So all of the engineers will sort of work through this very basic development process. So sketching out an initial concept, evolving the maturity or the resolution of that concept, building prototypes. So we have a few 3D printers in-house. We have a well-stocked workshop, so we can build physical prototypes. We have a small test lab, so we can carry out some basic fatigue tests, some static loads, so we can start to get a feeling of, is the component or the assembly feasible, and then we just follow a test, break, improve and repeat process. And eventually, once we have the element of that design, whether it be a part or an assembly, we'll validate that with an external test house to the ISO 4210 standard, which is required to sell the bicycle. So traditionally, we've developed conservatively, which is a robust way of developing, but it's slow. What I wanted to do is to try and speed that up, especially with a lot of the structural work. Building frames takes time, so it can take weeks or if not months to have a new frame set with a modification to start a new test. So I've thrown in a few simulation iterations in there, which is relatively easy to do in theory. In practice, trying to get that early phase CAD out into a simulation tool is challenging, and that's where SimSolid really comes into its own, because you can be lifting that CAD out in various states, with various contacts, with various clashes, and start to develop through using the simulation tool. So similar process, but trying to get the engineers used to using that simulation package as another tool in their toolbox. So the type of simulation we're looking at again, very simple. I want to keep this quite basic. It's linear, static, and some fatigue analysis. We'll do a full frame set down to individual parts. I'm really keen to get the designers to just start to take the design away from CAD, not just models in the workshop, but to simply do a push and a prod approach to be able to understand the structural stiffness of the parts and assemblies they're working on. So our main drivers really are to lightweight part of the Brompton. When it's folded certainly in its luggage form, it's heavy, or it's heavier than we feel it should be. So part of the work we're looking at here is to lightweight. The other is developing new parts and assemblies. We're optimizing for a structural stiffness and strength. So this is looking at the frame set. So we'll take a full frame top-down approach. So here we've created a linear static model of the frame set. Relatively simple to set up, relatively simple to constrain all of the contacts. We'll take that model, we'll run it through some basic load cases, which we replicate here in the lab at Brompton. So we've got a series of 8 static loadings, which represent the riding conditions or the ride characteristics of the bike. So sometimes, for example, for rear end efficiency, we're looking at stiffness. Other times for horizontal comfort, we're not chasing stiffness, we're benchmarking against existing products. Again, steering position, which is effectively the torsional stiffness of the whole frame. Again, we'd be chasing stiffness. So very different objectives for each simulation. So I'll just run through an example that we've used SimSolid for here at Brompton. So this is the hinge clamp plate. It's a forged aluminium heat treated T6 part. That's fundamentally a critical part of the frame set. So it's used to clamp the 2 halves of the hinges together on the handlebar support and also on the main frame set. So what we were looking at here was the existing design is extruded and then like I say, forged. The designers were involved and wanted to change the aesthetic of that plate. So here we've got the original design. We just carried out a simple constraint on the hole, a static loading in 4 of the corners. We had a weight. We were tracking the von Mises stresses. We had a designer solution, so completely outside of any form of simulation. We were driving just the aesthetics. So some areas of wall sections, some areas of form were dropped. We reduced the weight, which was great, but we pushed the von Mises stresses in the corners here to an unacceptable level. So 2 or 3 iterations later, we managed to drive down those stresses in the corners, while marginally reducing the weight, but certainly not adding weight. So to optimize the design relatively quickly, this was a morning, if no more than a day's work, to then have a lot more confidence in the design than we had from the original designer's concept. So if I end this slideshow here, I'm going to open up SolidWorks because I want to run through a live demo now. So I'm going to start with SolidWorks. We use SolidWorks here at Brompton. So I've got a model here of a handlebar assembly. So there's about 30 or so components in here, from the handlebar, brake lever assembly. We've got a bolt in place here, which clamps the handlebar support to the handlebar. Hinges to the handlebar support and to the steerer pin. Fairly untidy geometry, plenty of surfaces what I've done, I've also flattened the structure just really for simplicity. But inside each of these parts, we've got an assigned material. So that's just an elastic series of elastic material properties. So Young's modulus, Poisson's ratio, and the density. So what I can do in SolidWorks, there's an Open in SimSolid button. We can click that, and then what that'll do, it'll open the assembly then into SimSolid. So it'll bring the assembly in. What it'll do, as Ken was saying, it will recognize some of the parts. So if we can right click on the assembly, we can show the bolts. So it'll highlight in this assembly, we've got 2 bolts. We've got an M8 for the hinge clamp plate, and we've got an M5 bolt there to clamp the handlebar support in place. We can also just check if there's any parts without the material. So it's just a quick sanity check. So there's no parts there without materials assigned. Now, the first operation to go through is to set the simulation. So we'll define a linear static simulation. And there it's created the linear static simulation. Now we want to define connections. So we'll run the automatic connection checker, and we'll keep the normal resolution for the moment. So that just takes a matter of a few seconds. So here it's defined all of the connections. So we can start to click on a few of those. And you can see if we roll down to some of the connections in the brake lever. Further down here, we've got some connections in the hinge assembly. So the majority of these connections at the moment are bonded. If we want to change those to sliding, we can right click and edit the default condition and move to sliding without friction contact, still keeping it in the linear static realm. So for now, I'm just going to leave most of these in the bonded condition. So the next step is to define the spots for the load case. So what we're going to do here is we're going to set up a out of phase loading on the handlebar. So we're going to first of all constrain at the handlebar pin. So we're going to put a boundary condition on the handlebar pin here and selecting that face. So that's now fixed. Next, we're going to put a couple of spots on the handlebar to create the loading positions. So I've already got allocated a couple of spots there, so I'll add another one in just to demo how easy it is to put the spots on these surfaces. So we've got one there. Let's show those. And then we can add one on the flip side. Just flip that over. Hide the lever. And we'll add another spot on that surface. Okay, so we've got 4 spots. And now those spots are going to be used for defining the loadings. So we're going to put a force on these spots. So here we're going to apply a negative 270 Newton loading to be pushing down, and then a positive on this spot here to be pushing up. So we've created our loads. We've created our constraint. The next is to identify the bolts and create bolt loadings. So we want to tighten these bolts. So we know we've got 2 bolts in the system. So we click on the bolt. It's already recognized the bolt. So we add in the pitch of the bolt. So it's an M5, we'll put in a 0.8 pitch and 2 Newton-meter torque for this bolt. So that then is added into the load listing. And there's a nice graphic on there to show you the bolts loaded. And we'll do the same for the M8 bolt. This is a 1.25 pitch. Would add 4 newtons of torque, Newton-meters of torque on that bolt. So we've got the materials, we've got the geometry, the materials are assigned. We've defined our spots, defined the loadings, set our ground constraint. In this particular simulation, we've added in bolt loadings too. So now we can go ahead and run the simulation. So now it's defining the result display, and that is complete. So you can see it's a matter of seconds before we have a series of results. We can go into our result drop down. So if we have bolts, one of the nice features is the axial shear forces, bending moments of the bolts. We can go in and analyze those. We can get a visual display of some of the results. So I'll drop into just a displacement first. And for mysis stress, just noticing actually I'm missing the legend on the screen. I don't know if you can pop in, Ken, and if you're listening, to be able to bring up the legend.
It probably popped on your other monitors. Where's that?
Yeah, it's not on there either. It's
it might be behind.
There we go. There we go. It's just hidden behind there. Yeah. So let's go back actually to the displacement magnitude. There we go. Displacement, and then there we go. That's hiding there. So we can go in and we'll set true deformation, because actually the displacement is it relatively large? Nope. We can increase the deformation just to get an idea of the displacement there. If we zoom in, we can get an idea and see the bolts preloading on the handlebars. Then you can see the bolt preloading down here on the hinge clamp plate. We can drop out of there and have a look at some of the von Mises stresses. I'm just going to do that again. This is hiding. Again, we can play around with some of the scaling if we want, just to highlight the areas where we're seeing peak stresses. So one of the great things with SimSolid, if I then run back into SolidWorks and make any updates or any changes and bring in a new assembly, it'll exist in the same model file. I can, for example, if I change the wall section thickness or a diameter of the handlebar support here, it'll bring in a new assembly in the same model file. I can set it up in the same way, set up the load conditions, run that again in a matter of minutes, and I can quickly jump between results to get a comparison of the two designs. That's something that's extremely useful. you've got all of your design iterations then sitting in one model, and you can go back, and any of those iterations you can modify the loading conditions. So, although brief, I hope that gives an idea and of an overview of SimSolid and how we're using SimSolid to really just speed up the design iterations of our designs. So I'm going to move back into PowerPoint because I've got one slide that I think I've shown, but this is just my summary of simulation here at Brompton, and the main tagline is, for me anyway, is trying to move outside of CAD with the design engineer. So the design engineers often spend many hours absorbed into the CAD, and I'm trying to change the mindset a little so they have a true appreciation of the structural, the dynamic behavior of the parts. And SimSolid really does allow us to help do that by, first of all, there we've got easy integration of the mechanical simulation into the design process. It allows the designers to easily develop a simulation-driven design, so they're driving their design through simulation as well as other requirements of the design, such as aesthetics. And it really does break down the barrier to using simulation. It's an easy-to-use tool. So it's an easy-to-use tool. It's very simple, very quick, and the interface helps usually. So we've got a very similar interface there to SolidWorks, and that helps break down one of those barriers. So I think that's my summary there of SimSolid. So I'll just roll on to my final slide and pass you back over to Pete.
Thank you, Jonathan. That's fantastic. Thank you. So almost at the Q&A session now, but there's time for just one last poll, which again should appear on your screens now. So you've heard from Ken, of course. You've heard from John giving a great demo there. So the question is, are you interested in further discussion about SimSolid with the Altair team? And you can actually select more than one answer here. So I have a technical question to discuss with a SimSolid expert. Perhaps you'd like a personal demo to see how SimSolid might fit into some of your models that you work with. Perhaps you'd like information about trials and self-paced training courses, or perhaps you'd like pricing information about SimSolid, or perhaps it's not something you want to look at just yet. So again, just as before, we're going to leave it a few moments to answer that question. And if you have already answered it, then please feel free to ask a question, type that into the Q&A box just while we wait for the last few people to click some selections there. Okay, so lots of questions coming in, I can see, which is great, and we're going to answer as many of these as we possibly can. Okay, so I'll close that poll now. So thanks for everyone who answered that question. That should close. I'll change presenter back to myself just quickly. Show my screen. Okay. Okay, so next step, just before we get to the Q&A, so next step is that we have recorded this session, so you can watch that again, and we will be sending out information about how to get a trial. We'll be sending some links out about the Nathan's article that Ken mentioned in his presentation at the start. But if you do want to jump ahead and crack on and download the demo of SimSolid now, you can go to altair.com/SimSolid, and you will see a section there called Download Trial, and you can do that today if you want to try it out yourself. Okay, so looking at the Q&A, so there's a lot of questions coming in. Hopefully we'll have time to certainly answer as many as we can. Anything we don't answer, we'll get back to you after the webinar. One question I have to ask straight away, because the person actually asked it just before the webinar started, was one for John here. But what do you think, John, are the skills most important to work as a designer in the bike industry today?
Yeah, okay, so I suppose it's potentially a mixed skill set. So we have, like I was saying, we have an industrial designer here, so someone with a good level of product design knowledge, experience of working on consumer products, but I think fundamentally a good understanding of the basics of engineering. So really just having a good understanding of the physical behavior of materials, structures, that's a huge help. So that's a huge help and a good start.
That's great, thank you, John.
Okay.
So Ken, one for you here. Someone asking about links to designing experiments or optimization techniques. So does SimSolid interface with other tools to help with optimization work?
It doesn't. I mean, there's no direct links today. You can obviously do manual links, but we're looking certainly in the partnership here with since we've been on board with Altair, that would be a direction for us to go in.
Okay, thank you, Ken. Question here about what sort of computer specs does it take to run SimSolid? What does that spec look like, Ken?
Yeah, we wrote it to be multi-threaded from the very beginning. So it'll take as many threads and cores as you have, but you don't need a big machine. And a desktop, a laptop machine is fine. You probably, the minimum requirement is 16 gig of memory and an i7 processor. So 4 cores, 8 threads, and it'll work great. If you have a really big model, 32 gig would be more than enough.
Okay, thank you.
I think one of the advantages, you don't need a real big, compute server kind of thing to run it.
Yep, that's true, Ken. Just to add something in here, that demo is run on exactly what you described as a minimum spec. So and it runs perfectly fine with that model of around 30 to 40 parts.
Thanks, guys.
Okay.
Another question here: does SimSolid support frictional contact?
Yeah, we do. You can do opening and closing contact with friction. That is a nonlinear analysis, nonlinear static, but we do support that.
Thank you. Another question here: how is the relationship between bolt torque and tension determined in the software?
Well, it's probably a little bit more than I can talk about here, but I can say that the whole technical description of how that's done, equations and all are in the help. So if you download the trial, just look under bolts and you'll see all the whole equations background right there.
Okay. A question for you, John, here. So was there any simulation performed at Brompton before SimSolid? And what software was used, and how long did it take for a similar assembly?
Before SimSolid, we were using the SolidWorks add-in, the simulation add-in, and a big part of the problem was it was being used predominantly on tube and plate models. So it was misunderstood. I think that's one slight danger of making it too simple, making simulation too simple to the user. So part of the training here is rolling out a clear understanding of simulation methodology in terms of setting up the model, using the correct element types. The great thing with SimSolid, we don't have to worry about the correct element types. So that's taken an issue out of the development of the simulation model. So yes, so it was the simulation add-in to SolidWorks was where we started.
Thanks, John. Question here is how long is the trial? It's 14 days, I believe. So if you go to that website and download the trial, you'll have it for 14 days. Is there non-linear contacts in SimSolid, Ken?
Yeah, there is nonlinear contact.
Okay.
Open and closing with friction.
Okay. Another one for you, Ken, I suppose here, which is you sort of addressed it in the opening, but is there any reason why a company would not replace its traditional FE software with SimSolid? How do you see that sort of relationship?
No, I mean, I really think it depends on the industry and the workflows. You know, we're been used quite a bit in the automotive industry. There's been some rapid adoption there, and you know, to go and replace an existing workflow takes many years in these bigger companies, right? But and that can certainly happen over time. I think the advantage, though, is you can use the opportunities. You can use analysis in a different way that was not possible before. So it's not so much replace an existing workflow; it's actually creating a new workflow that maybe provides more benefits.
Okay. Question from a SolidWorks user here. So, how does it work with the integration with SolidWorks? Is it a plugin? Is the question.
Well, yeah, we have two ways. What John was showing was a plugin. There's a plugin directly inside of SimSolid. I mean, inside of SolidWorks, it just pushes the geometry and the material properties through a memory socket into SimSolid. So that's one way. If you don't have SolidWorks on your desktop and all that, you can just say File Open and open a SolidWorks part and assembly file directly. So you can do it that way as well. The second way doesn't bring in material properties, though.
Okay, all right, thank you. So do the geometry import settings have a big influence on the results? Is one question we've had.
You know what we have in terms of geometry in SimSolid, we bring in solids, and then we bring in the surface faces, but then we create facets on the face. So the reason we bring in a faceted surface is it's just efficiency. It makes it more lightweight than having to bring in a heavy surface and solid model. That being said, the facets, I think the rule of thumb is you just need the facets to be, you know, visually the same what you'd expect. Of course, if you have 4 facets to define a cylinder, you know, it's not going to be very accurate. But if you have, you know, an adequate number around the cylinder, it's fine. It will solve the facet geometry, though. So, yeah, you need to be aware of that.
Thank you, Ken. Just a couple of last questions here because we're fast approaching the hour. So is there an equivalent to mesh refinement in SimSolid?
Well, yeah, that's that whole adaptive process. SimSolid actually has, in effect, automatic mesh refinement, but it's not just, you know, mesh refinement. Mesh refinement just says, let's just change the mesh size. This actually does adaptive refinement in local regions of the model, and it does it to minimize error in the reaction forces. So because of that, you get you know, a nice converged solution. There's also a number of controls that you can set. There's typically we have just a very simple adapt to stiffness, adapt to stress option. You can have some custom options where you can say, I only want to adapt in local adaptation in 5 or 6 parts. So you can even steer it even more refined if you want. So there is that is available. I think the point is that it's always on. You can't. It's not an option with SimSolid. Adaptivity is just a fundamental part of the solver.
Okay, and just one final one as we hit the hour. So our suppliers send a lot of CAD files, a lot of CAD as STL files. Can SimSolid complete analysis from an STL file?
Yes, it can read STL and solve STL, sure.
Okay, thank you, Ken. Thank you, John. So thanks to everyone who attended today. We will be sending out this recording, and that should arrive with you in an email coming out tomorrow morning. So you can watch it again. You can share with your colleagues. You'll also have details on the email of how to get your trial. Again, if you do want to get it now, head to altair.com/SimSolid, and you can find it there. So if we haven't answered your question, apologies. We're obviously a little bit up against it in terms of time, but we will make sure to send you an email with the answer to that question. So you'll still get that answered, just not live on the webinar today. So again, thank you for joining, and I'm going to close the call now. Ken, John, thank you very much, and speak to you all again very soon. Thank you.
Thank you very much. Goodbye.